All right. So before I get started with today's thing, there's a couple of good questions that came up yesterday after the lecture. So I'll kind of just briefly mention the idea behind this. So we had, when I was drawing these pictures in momentum space, right? I said, oh, imagine I have a square lattice, then I have some Brillouin zone. Okay? And I was kind of drawing these circles where I said, well, we are going to kind of start integrating towards the zero momentum, for example, for a ferromagnet. And one of the questions is, why are you taking circles when the underlying symmetry is a square? And really, the picture here is that you could kind of start with something that looks like a square to begin with, over that region. It's not something that's easy to implement analytically. Okay. But what you expect is that, if you want to have this kind of a behavior, you want to ask, well, is there some natural, thing in the action or in the energy functional that tells us that, that there is some particular shape that I should be choosing, right? And roughly speaking, you can kind of think of the thing that, appears containing momentum is the gradient terms in the action. So it looks to leading order, it looks kind of like this, and then there is other stuff which I'm omitting, right? And this naturally tells you that along the circle, you will have contours of, in some sense, equal energy or equal action, right? So you might think that that's a useful thing. Of course, if you're starting with a square, there's no reason to stop here, right? And in general, you will have terms which are of the form, something like qx4 plus qy to the 4 times phi q with some other coefficient. So let's say we had some stiffness here. This could be some other coefficient times phi q, phi minus q. And if I do this and I ask, well, what are the equal energy contours of this kind of a function? It'll look squarish. It'll break circular symmetry because this doesn't have circular symmetry, right? But on the other hand, you see from here that, if I look at this, as I go to smaller and smaller momentum, in fact, this will become less and less important. Okay. And so what you call, if I want to think of these as equal energy contours, will look more and more circular in the limit where I'm kind of zooming in towards q equal to 0. Okay. So this tells us, I mean, one important thing that this tells us, which, is this thing is that, even though I have a crystal that has, let's say, the symmetry of a square in this example, if I look at the physics near the transition where I'm looking at the physics at long length scales, in fact, I have a symmetry that corresponds to a higher symmetry than the symmetry of the problem that I started with. Okay, so these are then sort of examples of what you might call sort of emergent symmetries in the problem, where even if you had terms of this sort, eventually it's possible that terms of this sort become unimportant, and at the critical point or very close to the critical point, things look like they have higher symmetry than the microscopic symmetry of the Hamilton. Okay, so that's an important point, but for the purpose of what we were doing, I was kind of imagining that, let's say we've kind of gotten to this point where, we are not going to worry about terms of this sort, assuming that they are small already and we've ignored them at the outset. Yeah. Okay. So that's point one. The second point was, sorry, what was it? I'm blanking. Just sorry, give me a second. I wanted to circular. Maybe I noted it down. Yeah. So the other question was, if we look at kind of this process of doing the RG, right? We said we are going to come zoom in closer and closer to, for example, this point in a ferromagnet. Okay. But in the renormalization group flow, if you remember, we also said that as we keep doing this, as we keep zooming out, the interactions get such that, imagine this is J divided by temperature, which we are calling K in the capital K in the plots that I was making. As you keep doing this process, you're going to regimes where J over T is very large or very small. So this is the disordered phase, and that's the ordered phase, right? But if you keep doing this, you're also losing information in momentum space, right? And then the question is, well, what does it mean to have a disordered system? Because the way we think about a disordered paramagnet is you say, well, spins are completely random from site to site, right? And if that's the case, I should expect that things in momentum space will look completely flat Like if I look at the Fourier transform of the spin, configurations, it will look completely flat in momentum space. But that aspect is not being captured here. I don't see that momentum structure if I'm just throwing out whole chunks of momentum and just zooming in at q equal to 0. How do I know that this is a paramagnet if I lose the picture that things have to be flat in momentum space? I should be able to see that things are flat in momentum space, right? And so it's similarly on the ordered side, right? You want to see that there is something sharp developing, but beyond that, you have some correlation length for fluctuations, which are actually quite short. In other words, if I go deep into the ordered state and I flip one spin here, a faraway spin will know nothing about it. Okay. So similarly here, I kind of lose this structure that, there is some ordered, but around that order, the excitations are not correlated with each other on long distances. Okay. So the way you have to kind of think about this is the following, which is that, I should really think that, I'm starting somewhere very, very close to the transition point here, right? Where you expect that I have some fairly sharply peaked structure in momentum space that's centered at q equal to 0. And what we are going to do now is, as you do this renormalization, you might find that, this thing at q equal to 0 either comes down, it becomes kind of flatter, or it's going to become sharper, right? But I don't have this information away from there. If I do this RG for if I run it for very long, I don't have, I'm kind of also losing information out here, right? And so what people usually do, and this is not something we'll do, is to say, well, I can do the renormalization in, out to length scales, which are kind of comparable to the correlation length, where spins are kind of correlated with each other. And I'm trying to describe the physics of these correlations and how things scale as you zoom out. But at some point, I'll say, well, I should just stop doing this renormalization process, because at that point, my spin correlations have become relatively short ranged, which means I don't really have this kind of nice continuum picture of the lattice when I've zoomed out enough. And at that point, I should really be doing something like mean field theory or some perturbation theory on some problem, right? So the way to think about this is, you kind of do the renormalization up to some point, right? And once you've zoomed out on scales of the correlation length, I should really be trying to do some kind of mean field theory and try and patch these two answers together. So it'll be like doing mean field theory, but with some renormalized parameters in the problem. And the renormalized parameters will be gotten by tracking these RG equations up to some scale and then matching it onto something else that you would have to do beyond that point. So clearly you can't kind of, go through the flow all the way to, so I can't expect to recover kind of all the physics of the paramagnet simply by doing this renormalization process. Because this is going to go somewhere, it's going to flow very, very far away from my starting point. And lattice scale physics will be surely important here and there. Yeah? Okay. Good. So let me erase this. And let me then. So let's set up this Wilsonian renormalization, and this stuff that was worked on for this model that we will look at was done by Wilson and Fisher. Okay. And so the picture now is the following, that I have some partition. So let me start by, so we have some partition function, which is given by this integration over, all components of this field, e to the minus s. Fine. And our picture for S of phi we wrote down already was that it's some integral over, and I'm suppressing all the spatial dependence on the fields here, plus some We had all these interactions, and we said there is a uniform field that couples to, let's say, the component number 1 of the spin. Okay. And there's other stuff here. And from here, we went to momentum space, right? So we went to a momentum space description where we wrote this down as an integral over momentum. So this integral over Q is going to represent a d-dimensional integral over momentum with this factor of 2 pi to the d, and that will be what I'll use as kind of shorthand notation. Right? Integral over Q, and we have this 1/2 t plus kappa times Q square times phi Q, phi minus Q with alpha. That comes from Fourier transforming this that we did last time. Then we have this term, this field term is just completely uniform. So this just picks out the 0 momentum value. So let me just call it phi1 of Q equal to 0. And then we wrote out sort of what this interaction term was. And we said, oh, there are 3 different independent momenta that I have to integrate over. And we had, let me call it phi alpha 1, phi alpha 2, phi alpha 3. So this, sorry, B term. So the 1, 2, 3 refer to Q1, Q2, Q3. And then the 4th momentum is just -1, -2, minus. So it's minus Q1, minus Q2, minus. And in general, there are other higher order terms that are, yeah, sorry. In the strongly disordered, so far from the critical point, yeah. Right. So if I look at the correlations of phi of Q, so since this is a Gaussian type, so imagine I ignore all this for a second and I ask, well, what is the correlator of phi of Q, phi of minus Q, right? Then it's going to be 1 over this coefficient, right? And if T is very, very large, then this Q dependence is not important, right? So you're going to get something that's just flat. Correlations are flat, but in other words, if I were to take something that was completely random and I just average over many such random configurations and I compute sort of what the averaged spin configuration will look like, basically be flat in momentum space. Like every site is something. Yeah. Correct. So there are no correlations in position space, right? So that's, sorry, that's all I meant. Yeah. Okay. All right. Okay, so this is a thing we did. The other thing we did was that we assumed that we are going to start with some Brillouin zone, and we said, let's assume for a second, and this is only justified when I'm sufficiently close to this, so this point, where I've kind of zoomed in enough, but we can kind of start off by assuming that there is some cutoff scale, lambda in momentum space, right? And that scale is going to be roughly governed by just counting degrees of freedom. So just say the area of the square is the same as the area of the circle. That will kind of set for you some initial starting point. Okay. But we'll see that the physics that we're interested in will really not depend too much on this. So I could have imagined doing this process and getting some Landau theory where I could have started here and then started doing this process. Okay. So you can kind of have some cutoff scale in mind without kind of worrying about the precise geometry of this, how you're drawing the circle, for instance, right? When you're close enough here, I can assume that is like a circular cutoff. Okay. All right. So this is one. The second thing we did was to try and define sort of what we mean by slow and fast degrees of freedom. So we said that phi of Q less right? So the slow modes, and you can put like a subscript S or F, or let's put like a slow for slow modes and an F for fast modes, okay? So phi of this thing is going to be defined such that it is equal to phi of Q, provided Q is smaller than a certain threshold. And it is just 0 if Q is above that threshold. Okay. And by above that threshold, really, I mean that it lies in this interval lambda over B, in this interval. Okay. Similarly, I can define phi Q fast to be such that it's complementary to this. So it's 0 if I'm looking at, so B is right now very arbitrary, but this is going to be defined such that it vanishes, it has no weight when I'm looking kind of at small momenta, but it's equal to phi Q when I look at large momenta. So if we draw our circle, we are just labeling these modes as saying, well, everything here is fast and everything here is slow. Okay. And this boundary here, if this initial boundary was lambda, then this length scale is going to be, this momentum scale is going to be lambda. Is this fine? All right. So now we say, well, let's try and divide up the modes in this fashion, and let's write out sort of what this action will look like if I were to do this integration now in 2 steps. So remember, with the decimation, we said, well, let's integrate out all the odd spins, keep all the even spins. We are doing something similar here, except it's a little more better motivated, where I'm integrating out modes, which I think will be unimportant for the critical properties, and trying to keep the modes that are going to be eventually important for the critical properties. Okay. So these modes, the F modes kind of lie in this region, everything in that region. Okay. All right, so let's try and do this where we kind of do this for this action. Let me try and split this into separate pieces. So let's call, one of them is S0. So let me refer to this as this part of the action as S0. Okay. This part, let's call it some SH. It comes with the field. Okay. And this one here, and I'm going to ignore the others for a second. For now, let's call that S with the subscript U. It's coming from some interaction. Okay, so let's try and do this division for each of them. Okay, so let's try and say, well, what is S0 of phi? If I simply substitute, this definition for slow and fast, you would say, well, I should just substitute phi Q to be one of those. Slow, this will be a slow plus fast. So by definition, my phi Q is phi Q slow. Right, it's just a sum of slow and fast fields. Right, and now I can sort of substitute that here. Okay, and I can ask, well, what are the kind of terms I'm going to get? Right, so here you're going to get terms which are the sort phi Q slow plus phi Q fast, then phi minus Q slow plus phi minus Q fast. Just from expanding out this product, right? And you see from here that there is no meaning to cross terms, because if phi slow is non-zero, then phi fast is necessarily 0, because these are non-overlapping intervals in momentum. So things which involve cross terms will not survive in this product. And what you're going to get is simply phi Q slow, phi minus Q slow plus phi Q fast, phi minus Q fast. And okay, I can bring in sort of if I want my spin labels, I would have sort of spin labels kind of coming along for a ride here. These extra component labels alpha. Yeah. Okay. So if I can do that, you see that for this one, you would say because it's at zero momentum, it's always only slow by definition. Okay. And so for a moment, we'll actually ignore this. I'll kind of tell you what happened, because under the process of doing this renormalization, removing high energy modes, nothing is really going to happen to this one. This will remain untouched, right? All the way till Q equal to 0, this is not going to be changing at all. So we'll omit it for now, but just keep that in mind that this is some slow field which has no fast components at all. This one is more complicated because this one you might say, well, I could have a situation where, I could have two of these being slow, two of them being fast, or, I could imagine, oh, maybe three of them can be fast, one of them could be slow. So imagine I have three momenta that come in. Imagine three particles meet such that their momenta are coming in at 120 degrees. They're all kind of fast momenta. And when they meet, the net momentum is 0, right? So you could have something like three fast momenta and one slow momentum, and that's possible, right? Or you can have two of these being slow, two of them being fast. So any possible combination is in general allowed for this kind of term. Okay. So this, leaves the slow and fast modes, unmixed. And then the problem with this nonlinear term is it's going to mix the slow modes and fast modes in the physics. Yeah. Okay. So now we want to ask, what happens if I try and, do this? Let me ignore this for a second. And let's do, this process of renormalization with just the first two terms in the problem. And the second one, as I said, really doesn't amount to doing anything. Okay. So let's try and do this for this first term, right? So let's say I do this for S0 plus SH of phi. Then you say, well, what am I going to get? I'm going to get something where this goes from 0 to lambda by B for the slow fields. From here, right? For the fast fields, you're going to get the remaining. Sorry, this is a Q integral, right? And this just gives you the, the radial component of the momentum. Going from lambda by lambda, T plus. And you'll have some coefficient of spin component alpha. And then finally, you have this minus H times phi1 of Q. And now our process of decimation, or the analog of decimation, is to say that, well, I'm going to divide my integration here is going to be a d phi q. Slow and fast modes. Okay. And we're now going to write out these pieces here, right? So let's think of this as S0 slow. That's this piece here, right? Then there's an e to the minus S0 fast. Okay, that's coming from the second part. And we have this e to the minus SH, which is slow. So let me just kind of label it with a slow. There is no fast component. Yeah. So now we want to do the analog of decimation, where we say, well, I'm going to do this integration in two steps. So I'm going to first integrate out the fast modes and then integrate out the slow modes. Okay. Or more precisely, we will integrate out the fast modes and ask, well, what does the effective Hamiltonian or the action look like for the slow modes in the problem? So you see that these are actually completely independent. So all the slow modes don't talk to the fast mode. So in principle, I could just do this integration by separating out pieces here where these two kind of come with the slow integral and this one comes with the fast integral, right? And you see that, okay, if I do the fast integral, I'll just get some number. Okay, that number has a meaning. It is just the partition function of the fast modes in the problem, right? Doing this part of the integral, in other words, doing this part of the integration, right, is just going to give me a partition function for the fast modes. And if you remember, this is exactly what we saw when we did this decimation in real space, or this, removing half the spins in real space. There were certain factors Z naught that we found, right? And one should really interpret that as the partition function related to the degrees of freedom that I've kind of removed in the problem. So this is exactly the analog map. You're going to get some fast component partition function. Okay. So all of this now, by the way, is being done with u equal to 0 for the moment. Then you say, well, I have to do the remaining. But for the remaining, you see that, oh, there is some meaning to this action. So the action now is going to be just dq phi slow e to the minus s0 slow e to the minus sh, which is also slow. Is okay? And so now you see that, okay, I'm only integrating now over slow fields and I have the slow action. Okay? And now I can ask, well, can I compare, how these interactions have changed here versus, what I started with in this problem here, right? So here, when u was 0, I was defining this problem by having a certain reduced temperature T and a certain stiffness kappa, right? And I want to ask, well, how have those changed when I go from there to the scale? Okay. And you say, well, I'm not done anything, right? So those numbers will not change. Okay. So if I look at S0 slow, you would say, well, S0 slow is exactly this one here. The numbers have not changed. Okay. But what has changed is the fact that my lattice is no longer defined the way I thought it was, right? So in the problem on the real space, when we were doing this, we'd say, well, my new lattice has points that are spaced apart with a distance 2. Okay? And I have to account for that when I accounted, for instance, for the free energy of the problem or the free energy density. I saw that, I have to account for this fact that my lattice has now looks like it has fewer degrees of freedom than what I started. Okay. So in order to actually put them on the same footing, you have to end up rescaling your momentum. Okay? And that is equivalent to actually doing what we did when we thought of scaling and so on. When we are comparing the free energy densities before and after, there was a factor of b to the minus d that we found yesterday, right? So the same way here, in order to make this comparison correct, I have to actually scale the momentum in this equation here in order to make sure that the cutoff looks the same. In other words, I'm sort of counting as if it's the same degrees of freedom in the problem. Then I can make a sensible comparison between whether things have grown or things have shrunk. Okay. So what we're getting here now is that if we do this, then we are forced to do the following, which is I have to define a new momentum. Okay. And that new momentum has to be defined such that it's given by so I have to define a q prime, and q prime is going to be defined such that it's q times b. So is it okay? Or yeah. And if you do that, then what you're going to get from here is that this quantity, sorry, maybe I should write on the side. Maybe I don't need this. So if you do this transformation, now I can ask sort of what is this S naught slow? What does it look like? This is going to look like an integral over Q prime that goes from 0 to lambda. Right. The Q gets cut off at lambda by B. Q prime gets cut off at lambda. Okay. These things are not changing, so it's still half of P plus KQ square. That doesn't change, except Q now has to be replaced by Q prime, right? So we are going to replace this by Q prime squared divided by B squared. Okay. And finally, we are going to have this field here is going to be some phi slow of Q, but it's going to be phi slow of, let me write it as phi slow alpha of Q prime divided by B and phi slow of alpha of minus Q prime divided by, these are vectors. I just mean that the magnitude goes from 0 to lambda. Let me just try. And finally, this piece here, nothing has happened because I could have called this as Q prime or Q. You'd say, well, it doesn't really matter. So this one here is going to be H times phi, phi 1. It is slow by definition. And I could call this at Q prime. Yeah, sorry. Oh, I'm sorry. Sorry, you're right. Okay, thank you. And that's going to change as well. Thank you. But maybe this shorthand is a bad idea. Okay, so we had this element here with ddq, and now I have to replace it by ddq prime. So this is going to give me exactly what we wanted, namely that this is going to give me a factor of, so this was q prime divided by b. So this is going to give us the b to the minus d that we found also in the when we were doing the scaling or the real space version of doing this renormalization process. Yeah, is this fine? Okay. Let me erase this. Maybe we'll come back to this later when we need it. So now, okay. So now I say, well, but these fields are not, this action doesn't look like the action I started with. These arguments look weird because they have this extra factor of B. Okay. And the way to we're just going to redefine new fields. And we're going to redefine new fields such that this phi S alpha of Q prime over B is going to be defined as some factor. This Z is not the partition function, okay? But it's going to be defined as some factor times phi S of alpha. Let's call this some new field with Q prime. So this just redefines this field itself. And in general, this is going to be multiplied by some factor Z. And we'll kind of figure out what the Z is or how we want to choose this Z in a second. But right now, this is just redefining, if I have fields defined as function of Q prime over B, I want to just redefine new fields which are functions of Q prime rather than functions of Q prime. Yeah. Well, this is some completely different, so if I say that this is some function, this is just redefining what the function is, right? This is not, this is not the same, sorry, unlike the earlier case, right? So in the earlier case, when we were doing the scaling analysis, we said that there's a free energy, which is a certain function of its parameters. And we said, well, I can take that same function and just rescale all the parameters and multiply it by something outside. That's not what we're doing here. Okay. There's just some new function phi twiddle that has nothing to do with phi, the precise functional form of phi in general. Okay, this just redefines the argument, and this just gives me my new function. Z is a factor that we'll kind of figure out if we need to keep it. In general, yeah. Right. So the reason we don't want to do this is that we will choose Z in a way that this action looks exactly the same as before. So I'll come to that in a second. Okay. So what we want is when we try and plug in this definition here, right? We want what we found in the case of the Ising model, when we did the 1D Ising model, we said, well, the model that you get, the Hamiltonian that you get after you do this, one-step process of removing all the odd sides, that Hamiltonian somehow looks exactly the same as the old Hamiltonian that I had. Okay, and so we want to be able to capture that. So we'll see what this Z is going to do in just a second. Okay? So if we plug it in here, so this S0 slow is going to be 1/2, b to the minus d times an integral 0 to lambda. Sorry, this is with q prime. These are integrals of q prime. I have explicitly written it down there. But this is now going to be an integral over q prime running from 0 to lambda. It's going to be t plus this k times q square, sorry, q prime square divided by b square. Now this factor of phi s, I can replace it by this new twiddle, new field, except this comes with this extra factor of z square times phi twiddle alpha of q prime, phi twiddle alpha of q prime. And then this one here, to be consistent, I'm going to switch from phi to phi twiddle even for this one, right? So there's going to be phi 1 twiddle of this all slow fields. I'm not labeling them. Sorry, let's call them slow. Everywhere. So here, slow, but this here, of course, whether I call it q prime equal to 0 or q equal to 0 doesn't really matter, right? So this will be q equal to 0, but I will have, because I've redefined my field, this is also going to have a factor of z. I'm just doing this at all momenta, this redefinition of the field. All right. So now you say, well, this action, if I look at sort of the integral of the, sorry, this is S0 plus SH. Sorry, this is S0 plus. I kept the field there. This total thing looks like this. Okay. And now you say, well, now can I compare my initial and final Hamiltonians, or in this case, the initial and final actions, to see what has changed? Okay. So you say, well, okay, there is some coefficient t here. That t, let me now kind of call this my new t prime. That t prime is going to be t times b to the minus d times z square. Sorry. Z square. This kappa here will go to some kappa prime. And kappa prime is going to be the old kappa times b to the minus d minus 2 times z square as well. And finally, I have a field which also has become some new field. times Z. Correct. That we just assume that this overall function is defined with some arbitrarily scale Farad. So as Sanjeev said, we need not have had this at all. Okay. The reason to put this will become clear in a second. Okay. But this factor of renormalization kind of defines the relation between the old phi's and some new phi twiddles through this relation. Okay. And we'll kind of use the fact that we can choose this Z to make some things look simpler. It's just a number, right? It's just an overall number, yeah. This is for all Q prime, right? So for all Q prime, we are redefining this field, right? And in general, I need not have had the Z because, this is some definition of some function phi twiddle. I could have just called it this, right? The reason to put in this factor of Z will become clear in just a second because it gives us some freedom with what we're going to define in a moment. Yeah. Okay. So now you can see what's going to happen if this B starts changing. In general, B and Z are quantities that will depend on the scaling, right? Because this definition of the redefinition of the field, the Z could be some function of B, right? You rescaled it by some B, the Z could be in principle some B dependent function. And now we want to ask, well, can I define my notion of a fixed point Hamiltonian which doesn't change under renormalization? Okay. In other words, I want to ask, can I define this problem such that, under my rescaling, my Hamiltonian is not going to change? Okay. But you say, well, it's not true that the Hamiltonian doesn't change because, for T prime and H prime, we saw that that's not the case because, if my system sits on the ordered side, right, then I do want T to become more and more negative as I do this renormalization. I want to go deeper and deeper into the ordered phase. If I'm slightly to the right, I want this quantity to go larger and larger, going into the paramagnetic phase, become more and more positive, right? So I certainly don't want this to necessarily be a fixed point in general, right? If I set T equal to 0, on the other hand, we know that this will be a fixed point of the problem, and that's going to correspond to the critical point. Okay. Similarly, H in general, if I apply a magnetic field, it's going to grow. The effect of the magnetic field is going to become larger and larger at longer length scales. But I know that if I want to get to the critical point, I have to set H equal to 0 in the problem. Okay. So imagine we do the following. Let's say that I want to be able to describe my critical point, and I want to think of this critical point as a fixed point of this whole renormalization process. Then we are going to set T equal to 0. Okay. If T is 0, then T prime is also 0. It doesn't matter what B and Z are. It doesn't really care, right? Similarly, if H is 0, which I have to do, then H prime is also 0. But the stiffness is actually going to flow because the stiffness will not look the same at different length scales. Okay. In other words, if I try and impose a certain modulation in, so imagine I impose a certain magnetization modulation of a certain wavelength, right? Then you might find that there is a certain energy cost, which is what, this measures in some sense the energy cost to making modulations of the order parameter, right? If on the other hand, I look at the system at some other length scale, right? Then, making that same modulation, it looks like, oh, if I want to get the same amount of energy, in general, my, stiffness will not be the same. Okay. So what we want to do is, if we want to be able to, on the other hand, define this critical point as a fixed point of this problem, right? Which is what we were doing for the 1D Ising problem or under this, 2D kind of somewhat contrived way of doing this renormalization in the 2D lattice problems. Then we want to demand that this quantity doesn't flow either. And if we do that, then you say, well, I must choose this Z such that this part of the, this change coming from this factor is precisely cancelled by the change coming from this factor. Okay. So for stiffness to remain fixed, we are going to demand that the Z square is going to be chosen to be precisely B to the D plus 2. Okay. Or Z is going to be B to the 1 plus. This, I should say, is in some ways, it's a matter of convenience. Okay. You could imagine trying to, just say that, so what if kappa changes, right? I'm just going to let kappa keep changing and try and compute my correlations or whatever I want to in a theory that is changing as I go to different scales. Because you say, well, I know how it changes. When I go to different scales, I know precisely how it changes. It's just that this coefficient is going to keep changing, right? So if I want to compute a certain, after a certain number of steps, if I want to compute some correlators, you say, well, put in that momentum, put in that particular scale and do this calculation. On the other hand, it's convenient in this case to actually define the stiffness such that it actually doesn't scale and calculations turn out to be somewhat easier in that case. Okay. So we can kind of, keep this fixed. And in that case, we actually have this notion that there is a certain fixed point action for this problem. In other words, if I'm at the critical point, I have tuned this to 0, I have tuned that to 0. Okay. And I can say, what is my fixed point action corresponding to this critical point? Okay. And that fixed point action simply corresponds to, so I have set this to 0, H is 0. I have set T equal to 0, so I don't care about it. So my fixed point action just corresponds to basically the gradient term in the problem. So the fixed point action is just 1/2 times kappa times this integral q squared times phi q, phi minus q. Okay. So it's like a pure Gaussian theory at this critical point. Or if you want to go back to real space and rewrite this, we can kind of rewrite this fixed point action by saying that, it's overall space, some grad phi, and you can put in sort of indices. Okay. And if you use this, now you say, well, I can calculate all possible correlators, and we'll kind of look at sort of examples of the starting in a bit. But you can calculate correlation functions of phi if I tell you that there's a certain fixed point action, kappa is some number. Okay, and I can calculate all fixed point correlations and kind of figure out, at the critical point, how things are going to behave. Okay, so this is the critical fixed point. In the point. Is this fine? And under this particular way of doing the renormalization, this action is left completely invariant. Okay. If this were to change, if I did not pick Z, then this will keep changing as I do the flow. And then I have to kind of calculate appropriately without these factors of Z. I have to sort of calculate what my correlations are. Okay. But this then defines for me now my fixed point action corresponding to the critical point. So if I'm at the critical point, I can use this to calculate all properties. Is this fine? Yeah. Functional form of? So if I'm looking at this fields, right? So if I'm looking at this field at the end of the day, if I'm redefining this field in this fashion, the correlators of phi twiddle are going to be given by looking at, so maybe I should have called this phi twiddle or something for the purpose of this one. The correlators of phi twiddle are going to be defined by the 6-point action. Okay. And the precise, power law scaling will be sort of captured by this physics. All right. Okay. So now you can ask, well, this is at the critical point. I've kind of tuned these two to be 0, right? And you've made this choice, this particular choice. But if I make this choice, and what if T prime and what if T and H are not 0, they're slightly away from 0, and I can ask what happens to the physics of the problem in that case. Okay, so let me erase here. And let's kind of ask what happens if T and H are not precisely 0. What's going to happen? Okay, so T prime is now going to go like T times B to the minus D. And we kind of figured out what Z has to be. Okay. So Z square, which appears here, is B to the 1 plus, sorry, Z square, which appears here, is just B to the D plus 2. So this gives us T times B square. H prime is going to be H times Z, but Z is just B to the 1 plus D by 2. So this is just going to be B to the 1. And so now you can say, well, let me try and plot what this does as I keep changing B, as I now kind of keep going away to larger and larger length scales. And if I were to stay in this two-dimensional kind of plot with H or HT. Right. H, let's say, is always positive. I'm applying the field with some given sign. It doesn't really matter, right? And what you find is, so this is my point that I had kind of said is my critical point, okay? And you find that both after scaling, both these quantities will grow if they're slightly away from 0. Both of them are going to increase under this renormalization process, okay? And so what you're going to get is something that looks kind of does something like this. It's all going to go away as I go. And that's fine, right? Because we know that if I want to get to this critical point, I actually have to tune two parameters. I have to set the temperature to be precisely some value, and I have to switch off any magnetic field. Only then I will be accessing this critical point, right? And this is just a physical thing that, if I apply any of these perturbations, I'm going to be taken away. I'm not at the critical point anymore. Yeah. So this looks fine. And now you can say, well, from here, I can try and, go back to what we did earlier. Remember that we defined that, how these parameters scale, in this case, the temperature and field, how they scale in some sense tells me those things in this homogeneous scaling function that we wrote down. So remember, we had that, T prime goes like, was going like B to some YT times the old temperature. Similarly, H prime was some B to the YH times H. Okay. And we had worked out certain exponents, like for example, the exponent nu was 1 over this YT. Right. So here we are able to read off what YT and YH are. So this particular thing so far tells us that YT is simply 2 from here. And YH is simply 1 plus d by 2. And now I can kind of read off, sorry, I'm not sure if can someone read off for me sort of some of the other exponent? Okay, maybe I have it. So we wrote out sort of what nu was. So nu was 1 over yt, okay, and yt is 2, so this is just a half. So that tells us that the correlation length grows like the 1 over square root of the distance to the critical point, right? We also calculated last time sort of what gamma was in terms of these quantities. So gamma, remember, was actually, let's forget gamma. Okay, so gamma is twice YH minus D divided by YT here. So that gives us, 2 plus D from twice YH, 2 plus D, and then I subtract off D, so that gives me 2 in the numerator, and YT is 2. So this gives us that gamma is 1. Okay, this look kind of Landau-like exponents, right? Mean field-like exponents continue to be true here. Okay. We can look at some other things, like, for example, let's calculate beta. Okay. So beta was given by, sorry, actually, I don't have the expression for beta written out here, but I think it was D minus, can someone just double check? I think it's D minus YH by YT, is this correct? Or this is fine? Okay. And so D minus YH will give me D by 2 from here, D by 2 minus 1. Sorry, is this correct? Divided by YT is 2. Okay. Let me see if this is D by 4. Yeah, so this is fine. Okay. And I'm going to rewrite this in the following form, rewrite it in the form where this is the mean field value, plus clearly there are corrections because it's no longer half. Okay. So this looks like it requires corrections, and the corrections are of the following form, which is 4 minus D divided by 4. So this is the expression. This is what, I'm kind of can simplify it to this form where it is half is the mean field exponent, and this is the correction to this mean field value. Yeah, sorry.
So you mentioned a different value of Z.
Yeah.
Then it would look like the exponents would change.
Sorry?
They might take a different choice for Z.
Right.
Then you get T prime.
Right, but then also this is flowing. So I'll have to sort of calculate things differently because this is no longer at a fixed point. So remember what we did was, we took our homogeneous part of the free energy and we said that, the homogeneous part of this kind of singular part of the free energy was some homogeneous function of its various variables. And we said that if it reaches its fixed point, I just set it to a number, right? But if it's not equal to, if it's scaling, as it does here, the answer, your free energy functional, okay, maybe this partly answers your question also, which is that the free energy functional that we wrote down, right, depended on all the parameters and how they scale, right? So in particular, we said, well, I can certainly set T to be 0. It's not flowing anymore. I can set H to be 0. It's not flowing anymore. But kappa is still flowing, and it's going to flow like, this thing here, right? So in general, let me pick some other value of Z. Z is B to some other power. Then this will tell me that, oh, kappa flows as some power of B. Okay. And now imagine I try and use this to calculate certain correlations or certain responses in the system, right? Then the question is, the answer might depend on how this is going to flow to 0 at the end of the day, right? So if this reached a number, then I can forget about it. It just becomes some function with a fixed point value here. It's going to become some f of 0, 0 kappa, right? But if it's continuing to flow, then the answer for my free energy is going to keep changing at different scales. Because if my stiffness gets larger, it's going to cost more and more to kind of make any deformations. Similarly, if the stiffness keeps getting smaller, if the stiffness tends to vanish, for example, it'll look like, oh, my spins become decoupled at long length scales, right? So how you sort of compute your responses will depend on, first of all, the flow of this quantity, and the fact that, if you naively set the stiffness to 0, you're going to get that the spin correlations will have some, will get completely uncorrelated to do something. So you can't naively set. So imagine for a second that I chose, imagine I chose Z equal to 1, right? Then this looks like, oh, kappa is flowing to 0, right? But I can't set kappa equal to its fixed point value, because there you say, oh, it goes to 0, maybe the fixed point value is 0. But if I look at the free energy at 0, you'll say, oh, there is no cost to making any deformations. Okay. And so you're not going to get anything critical at all at the end of the day. So in fact, this function here must be some singular function such that if I just set this argument to 0, it's going to blow up or do something else. Right. So this might go like, 1 over, so for example, something like this, 1 over kappa. Let's say it goes like 1 over kappa, then this is going to go like 1 over some kappa that's getting smaller and smaller. So my free energy is going to blow up or do something, right? So the precise dependence, so here I'm safe with setting t equal to 0, h equal to 0. And I want to make sure at the end of the day that if all other quantities are flowing, when they flow to the fixed point value, that things are actually safe. Okay. And kappa flowing to 0 is not safe, because that's the only term that's actually preventing spins from becoming uncorrelated in this particular case. Yeah. So.
Right now, all the whatever I get, like I have a 5 squared, I have a 5, 6. But what I'm expecting is that once I fix my Z so that kappa stays the same and T and H become relevant, the other directions, like the 5-4 direction is not included, or 5-6, they become irrelevant, or
they may become irrelevant. We don't know. Yeah.
Because otherwise we need to protect.
Correct. So we'll come to that in just a second. Yeah, but is this fine? So, when we did this analysis, assuming that the free energy is some homogeneous, function of its kind of various dependent kind of variables that appear, we also implicitly made that assumption that setting those numbers to the fixed point values is perfectly safe to do, right? But in a case like this, where this is the only thing that's controlling your, your free energy or spin correlations, you can't just set it equal to 0, or you can't just set it equal to infinity. Right. So the only time you're going to get sensible answers, for this kind of an analysis, is if this number actually does not change, it goes to a fixed point which has a finite strength, and then all correlations you can kind of compute safely without worrying about them kind of changing with scale. Yeah. Otherwise, you have to kind of worry about what is the precise functional dependence on this variable. You can't just set it equal to some number. Is this fine?
You obtain the correspondences by equating some sense of free energy after rescaling.
Yeah.
So you could say that, well, if I don't redefine the field, where is just rescaling the field?
Z is rescaling the field.
Don't do that, I can still get the same free energy at value. That's what we are doing. You're getting the
Say again.
So you're equating the free energy before and after this lambda.
Mm-hmm.
So, but if I can still get the same free energy without using any Z. If I rescale my field.
Sorry, so this is a field rescaling, and you're saying let's not rescale the field. Yeah. So imagine you don't have the Z, then you're going to get this particular free energy where kappa is going to be this kappa over B square. That's fine. And you can compute the free energy as a function of various parameters, and you will get some kappa that's a scale dependent stiffness. That's fine. That's okay. There is no, you're right, there is no problem with this. I can kind of do this analysis, and I will find that my free energy depends on things like the temperature and the field, and it depends on some scale dependent, there'll be a scale dependent stiffness, right? The only question is, if I want to keep doing this RG and I want to ask, is there a certain fixed point at the fixed point or very, very close to this fixed point, arbitrarily close to this fixed point, can I kind of say something about the thermodynamics of this problem, right? And it's easy to do if this is a number, because then this is some function and all the t and h dependencies we can analyze the way we did last time, right? We would say, okay, this function with this argument set equal to a number is some new function that only depends on t and h. Okay, so imagine I did not set t and h to 0 for a second, right? So this will be some t b to the yt, some h b to the yh, and something, right? What we did last time was we said, well, I'm going to assume that all these parameters have reached some number. This complicated function of many arguments reduces to a function of just 2 arguments. And then we did all the analysis of exponents, right? But if that's not the case, then I have to keep this extra factor, see how it flows, and include that in doing the analysis. Right. So it's just, then it's kind of a harder thing because now I have to worry about how my free energy depends on this third argument as well. And you can do that, but for simplicity, it's easiest to keep this argument fixed in the problem. Yeah.
And it that's at the t dash is not varying, like z is equal to t raised to my d by 2.
So z is b raised to d by 2. Or
Think that t dash.
from here.
Saying that z is t raised to d by 2.
Or to keep this fixed.
That fixed.
Okay.
K equals to h.
But k equal to 0, h equal to 0 is actually not giving you the right physical critical point, right? Because once k is 0, then this action becomes completely local in space because there are no gradient terms. Every point in space, I have some phi square and phi 4, for example, right? And the next point in space knows nothing about my field here, right? So you will get no correlations at all between the field here and the field there. Right, so it'll look like then I could take not just, so that's not like an overall Z2 symmetry. It'll become like at every point phi, I can kind of arbitrarily flip my spin. It'll become like a local Z2 if I don't have gradient terms. It'll look like a local problem at every point in space. Right? So it's unphysical to just set this equal to 0 or choose your scaling such that this vanishes, will not give the correct physical critical. This is fine so far? Okay. So you say, well, I have kind of made some progress, it looks like, okay, and this turns out not to be the case. It looks like I've made some progress. I have at least managed to find, oh, there might be some exponent beta that, deviates from mean field. And so you might think, oh, kind of on the right path, doing what you're doing. Okay. And that turns out to be, not correct. And the reason for that becomes clear when we kind of actually keep track of the fourth order term. So I've erased this, but let me just kind of write out what the fourth order term was here, right? So the form of the fourth order term we had was u times this integral over, 3 momenta. And let me schematically just write it as phi, 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 phi. Okay. Without kind of worrying about subscript momentum labels and so on for a second. Okay. And let's ask, well, what is going to happen to this term when we go through this entire process, right? Where we divide it up into slow and fast modes and, take into account in some way what the fast modes are doing and so on, right? But at the very simplest level, you might say, well, there is mode mixing, right? The fast modes and the slow modes will talk to each other because this is some nonlinear problem, right? But let's for a moment just throw away all the fast terms even, right? So you just say, well, I'm going to take only this part of the interaction that couples the slow modes to each other through this. Okay. So what is that going to look like? It's going to look like some phi slow, phi slow, phi slow, phi slow. So it's one interaction of the many that you want. This will be certainly one thing that will exist in the problem. Okay. And this is the only term that will look like the old nonlinear interaction, right? Because the other ones will be like phi slow, phi slow, phi fast, phi fast. If I integrate out the phi fast, it will look like I'm left with the product of two slow fields, right? That doesn't look like an interaction term, right? This one looks like the original interaction term, right? So let's kind of ask what happens to this one under this process. And you say, well, what am I going to do? This scale now runs over 0 to lambda by b. Okay. And now I'm going to do exactly what we did before. We are going to rescale these momenta, and we are going to rescale these fields. Okay. And what is that going to give us? This is going to give us a factor of u, right? And as pointed out, every time I change my momentum, I redefine my momentum, I was getting a factor of b to the minus d, right? But now I have 3 of these momenta, right? And so if I go from Q1, Q2, Q3 to Q1 prime, Q2 prime, Q3 prime, I'll get a factor of b to the minus 3d. Okay. And now each of these fields is going to get a factor of z because of this choice here that we have made. Okay. So if we stick with this choice, then I get 4 powers of z, 1 from each of them. Okay. And so this is going to give me that u prime, the new interaction, okay, is going to be u b to the minus 3d times z to the power of 4. But z to the power of 4 is just b to the 2 plus d. Did I get this right? 2 plus d. Maybe I'm missing some factors. Hang on. No. 3 powers of momenta. Sorry, just give me 1 second. Something wrong with what I just. Sorry. Oh, I'm sorry. Sorry, I should be. Sorry, I was doubling this one. Sorry, I should be doubling this. Thank you. Sorry, this was z. That was z squared. Okay. So if I square this, I get b to the 4 plus 2d. So that's that factor that appears here. Okay. So this quantity is going to be u times b to the power of 4 minus d. Okay. And so now you say, well, let me kind of try and do this by putting in a third axis here, which is u. Sorry, my axes and my flows are all kind of getting mixed up, but this is the, this is my, I'm trying to draw like a 3-dimensional plot here. And these were just kind of the various flow lines in the plane where u was 0, right? And now I have turned on a u that's non-zero, right? And what you find is that the place where we thought mean field theory will not work is where d is less than 4, right? And this quantity is then positive, right? And you find that, things begin to flow everywhere, in 3 dimensions, it's all going to flow kind of radially outward. Starting from this point, a deviation in any direction is actually going to take me away from it. Sorry, not a very good drawing, but you get the point, okay? And so what this tells us, in fact, this point, which I thought was a critical point, in fact, does not look like a critical point anymore, because, not only do I have to tune t equal to 0 and h equal to 0, it looks like I also have to tune u equal to 0, okay? And you can do this now. You can say, well, why stop here? I can try and look at other terms and ask. And in principle, you might say, well, maybe this happens for more than these parameters. Maybe other things become important. But at the very least, we know that this one becomes important here. The moment and in any dimensions less than 4. Okay. So you find that this whole notion of, this looked kind of promising, where I thought beta was becoming, a way different than half, and I thought, oh, that looked nice. So in dimension would have reduced beta from half to something. But on the other hand, we find that the very notion of this critical point gets destroyed if we do this. It's no longer a critical point. So then you say, okay, maybe what I have to do is actually I have to work harder. But before that, it's kind of useful to kind of recast this in a slightly different form where we kind of write out these flows in a slightly different manner, and we'll do that. But are there any questions about this? Just this last bit that I was saying. Okay. So before we sort of proceed, we can just take this piece of information that we have here. And try and recast it in the form where we are now actually thinking of flow equations rather than kind of writing out something that looks like some iteration where B was some number. Let's try and really write out these equations in the form where I'm thinking of doing some flow, which is kind of smooth. Okay. And so the way, Wilson realized that, one way one can do this in momentum space, right, is to imagine that, I can choose my B such that instead of defining, some jump between things that I'm going to integrate out and things that I'm going to keep, we can do this such that we do it one tiny slice at a time, right? So it looks like a bit like an onion, where you imagine you're kind of, peeling this onion and you're kind of going towards the center. Okay. And so if you do that, you might say, well, I can choose B to be such that, at every time I'm integrating out this little slice, integrating out the next slice, and so on. And each time, of course, in this process, the way we are doing it, we are kind of, expanding this bubble back to its original size each time, right? But the idea is that you're kind of integrating out sort of very, very thin layers each time. Okay. So what does that amount to? That amounts to saying that my lambda by B, I should really think of this B as something that's slightly bigger than 1, so that this slice is a very thin slice. Okay. And so you really view this as, lambda over, 1 plus some small change, some delta L. Delta L is some scale, right? I mean, it's not some dimension full scale. It's some, scale in the problem, which, I'm going to keep increasing this delta L is like increasing B and kind of shrinking down towards the zero momentum. Okay. And now I can ask, well, can I kind of recast these as, differential equations rather than as equations where I'm just going to iterate and look at kind of things on different scales? Can I kind of recast these equations in the form where it's kind of looking at a change in U under a small change in that scale that's kind of zooming in towards Q equal to 0. Okay. So, sorry. Yeah. So delta, okay, so the way I'm defining it is like it's a correction to L, this B. So I'm going from, that's right. So I'm going from lambda to lambda by B, some fraction. No, delta L is much, much less than 1. Sorry. So this L is much, much smaller than 1. It's a fraction, it's a, yeah. So this is like I'm going to some lambda minus lambda times delta L, roughly, if I expand in Taylor expand. Yeah. Sorry, that's a 1. Oh, no, lambda. That was 1. So this is the amount that I'm kind of integrating out in some sense. Right? So now you say, okay, so what does this mean? This means I can now try and substitute, this value for B is 1 plus some delta L. Okay. And I can try and recast these equations. So you write T prime is T times B square but B here is 1 plus delta L square, but this is, since delta L is infinite small, this thing is going to be T times 1 plus 2 delta L. Okay. And so this tells us that delta T over delta L, the change in this temperature parameter with respect to a little change in L is just going to be 2 times T. Which you can say, well, this looks like a flow equation written really now as a differential equation where dt dl is twice T. Okay. And this factor of 2, came from here. Okay. And this factor of 2 is precisely the yt that we wrote down. So yt here was 2, right? And it's the same factor of 2 that was here, obviously. It's the same factor of 2 that enters here, and it's the same factor of 2 that appears in the coefficient. Okay. So this coefficient, in some sense, tells us how fast or how rapidly T is changing when you move a little bit away from T equal to 0. Okay. We can do the same analysis for H, right? So dH, dL, and now you can basically read off the answer. It's going to have 1 plus d by 2 instead of 2, right? So dH, dL times H. And we can do the same thing for U. And again, this is number that's changing. So this looks like flow equations for these 3 parameters that entered into my Landau theory. And the fact that what I thought was a critical point is no longer a critical point because each of these directions is in some sense unstable, right? And so it looks like I have to tune many things in order to fix my problem. Okay. And the only way you can kind of imagine something happening is that this U becomes unstable. It looks like it's unstable, but eventually maybe it goes and this flow just stops somewhere, right? In other words, you think it is unstable. It starts off, you thought you were at the critical point, right? But U became non-zero. It started flowing. Okay. But imagine this flow could terminate somewhere, right? Then around that point, it looks like it's unstable. In other words, right now it looks like I started at U equal to 0, and along the U direction, it's flowing like this, right? But imagine this equation was not so simple, right? And in fact, the modified equations, whatever it is, allowed for the possibility that there are flows that look like this in U. Okay. Then what would I think? I would think that I started with my theory at U equal to 0. I turn on a small U, it started flowing, right? And if it started flowing, I said, oh, well, gone. This no longer describes my critical theory. But imagine what has happened is that there is a new point in the problem where this flows towards, right? Then you can say, oh, well, maybe this is the critical point I'm looking for, because around this point, if I try and make displacement, it flows back to this value. Okay, so maybe what I thought was the critical fixed point in my large dimensional space, I started assuming that my critical point was at T equal to 0, U equal to 0, and H equal to 0, and so on, right? Then we found, oh, no, that's not the case. But there is still open the possibility that there is a new point in this flow diagram where this thing will eventually go and sit. And if it sits there, then this point is attractive for this U perturbation. And you might think, oh, now if I make deformations, it looks like it's stable. So maybe that describes my physical critical point, not the original U equal to 0 point that I was thinking. Is this fine? Yeah. So we can ask, well, how can that happen with these equations, right? I mean, these equations are all kind of simple linear equations. And this is not going to happen unless somehow there was some nonlinear terms here, right? So this took me away, but I want some kind of restoring force that, brings this to a halt and kind of stops me somewhere at some point. Okay. So a simple kind of this thing would be, let's try and ask, what happens if this equation is modified slightly, and we'll kind of see precisely how to compute this. But imagine this equation is modified a bit such that I allow for the possibility of some U square coefficient, but this U square has to come with a negative coefficient such that when it grows very large, it wants to kind of push me back to not kind of explode, right? So what you really want is some modification of this equation such that du by dl, okay, is heuristically of the form some 4 minus d, which is a positive coefficient for 4 dimensions and less, or less than 4 dimensions. And I want something like some coefficient, right? Some g times u squared. Imagine I had this equation. Then you'd find that, oh, I can happily find a point where du dl is 0, where this u doesn't flow anymore under change of scale. And that's going to happen when two terms like this basically balance each other, right? So the two forces in some sense that are driving the change in u, if they exactly counterbalance each other, I have kind of found a new point where u does not flow anymore. Okay, and that's going to happen at a point u star from here, which is going to be given by 4 minus d divided by g. Okay. Right. So now this gives us some hint of the following, which is you say, well, I have been doing, whatever I want to do, and we'll set this up in a second now, is to say, well, I want to try, I don't know how to handle a nonlinear problem, right? The only thing we know from doing like, harmonic oscillator and kind of anharmonic oscillator and so on, is that we can kind of treat the anharmonicity as kind of a perturbation to my harmonic oscillator problem. Okay, so similarly here, we know how to kind of do Gaussian integrals or integrals which involve things like phi square, right? And if I want some integral like e to the minus phi square and I want to integrate over phi, I know how to do it, right? But on the other hand, I don't know how to do integrals over e to the minus phi to the 4 and so on. Okay, so that's kind of the direct analogy in some sense, except if I were to do perturbation in the anharmonicity, then I know how to kind of deal with this if I can do it term by term in perturbation theory. Okay, but this tells us that this perturbation theory assumes that certainly at small u I did this perturbation theory, or I didn't quite do the perturbation theory, but at least I included it, and I found that this thing starts to grow. Okay. If my fixed point happens at very large values of u, then it's like a theory with huge anharmonicity, and I don't know how to deal with it. Right. So somehow I want to ask, can I reach this fixed point, if at all? Can I get it to be such that at the fixed point, the value of u is not very large? Okay. If the value of u is not large at the fixed point, at the new fixed point, if it's there, right, then I can still do perturbation theory around that value somehow. Okay. Or you might say, well, at least it's good that if I start doing perturbation theory, I'm not going to huge values of anharmonicity. I'm going to end up at some small value of the anharmonicity. Okay, so this perturbation theory will stay valid in some sense all the way from here to here. if this point was very far away, you might say I start doing perturbation theory and perturbation theory breaks down before I get to that point, right? But if this point is very close to my starting point, then by doing perturbation theory, I can kind of follow the flow and get from here to the place that I want to go. This is fine? Sorry.
Now, if I do this, then the new delta K will just be G times delta K. But now
Correct.
we are arguing that if we were very far away from the critical point, thing that does not hold on. We need some other things. I mean, how do you?
No, what does not hold there? Yeah.
And then you could have the new delta K after code going to be just G times delta K.
Correct. So it's going to get larger and larger.
Not linearly grow.
Correct. It's not linearly growing, but the two cases that we saw were kind of things where we were doing this on the lattice, right? And in the Ising model case, we wrote down an exact recursion relation that we could just follow along. We were not trying to divide this into harmonic and anharmonic terms. It was some 1D Ising change and I could just solve it, right? When we did the 2D, we kind of, fudged the process such that it looked like an old Ising model, okay? And we didn't really solve for the thermodynamics or anything really. We just said, oh, there is some fixed point, right? But we saw that the answer, in fact, depended very much on how I do this in the first place. And clearly, it's a very crude approximation. And the only thing really we took away from there was the fact that, oh, there is some fixed point in the problem, but the properties around that fixed point are not reliable at all. Okay. And it's for the same reason that, you're doing something uncontrolled and not systematic. And if that's the case, then, you don't know whether the answer you're getting is right or wrong, or, how to improve, what to do is not very clear. Right? Here, what we want to do now is to now define this problem in a slightly artificial setting, as you'll see in a second, where we are going to demand that I should be perturbatively be able to go all the way from here to there without perturbation theory breaking down before I get to that point. Okay. And if that's the case, then, you kind of get a clue from here, which is that, well, G is, probably some number. I don't know if I do perturbation theory, we'll figure out what that coefficient is. But we see that there is kind of a fake parameter here, which can serve to make U star small, where you say, well, I can look at dimensions which are very, very close to 4. Okay. So this is not very meaningful if I want to do a 3D problem or a 2D Ising model. This is not very meaningful to say, well, I'm going to work near dimensions near 4 is not very meaningful. So the only thing we can hope for is that somehow if we do this at the end of the day, and if I make this dimension go close to 3, such that this number is not tiny, that somehow certain things will hopefully kind of stay the same. In other words, maybe the presence of this fixed point will stay the same. Maybe the structure of the flow will stay the same, but the precise, numbers that I get from there for things like critical exponents that we find, maybe we won't trust those. Yeah. So this is what, was this Wilson-Fisher idea, was to do what they call sort of dimensional regularization. In some ways, you want to kind of make your dimensions sit very close to 4, such that, you can assume that this U star fixed point appears at a place that's not too far from a perturbative regime, and then try and see if we can access some properties around that fixed point. Yeah. Okay. So let's do this. Okay. So let's. So in some sense, this 4 minus d being much, much less than 1 is kind of a good, way to control the perturbation theory. Okay. So let's redo these calculations, and we'll do this now Um, so let's try and kind of write out, so let's try and write out the action, and let's try and do this a little more systematically. Okay, so what we want now is my z was this integral over phi, and I'm just going to go directly to momentum space, right? So this is some phi fast, d phi slow. Okay, we had this e to the minus s naught slow, e to the minus. Let me drop h completely for a moment, and we'll bring it back because it doesn't really matter till the last moment. Okay, e to the minus s fast 0. These are the Gaussian terms. Okay, and then we had this e to the minus su, and I have to kind of divide this into fast and slow modes. Okay, so let's kind of do that and see what it looks like. Actually, let me not do that yet. Okay. So let's now say, well, what I want to do is I want to integrate over the fast modes and keep the slow modes for later. So it's d phi s, okay, e to the minus s0 slow. Okay. Then I have this integral d phi fast. And this depends on both slow and fast. So let me call it S and F. It has both slow and fast pieces. Okay. So it's d phi slow, sorry, d phi fast, e to the minus s0 fast times e to the minus s interaction that depends on slow and fast. Okay, and we've written down u as the fourth order term, but you could write down sixth order. All of it we can club together here if we wish. Okay, as some interaction that involves nonlinear terms of this. Okay. And so the trick we'll use, which is kind of useful for the level of calculation that we're going to do, is to imagine sort of multiplying and dividing by this factor here, right? So imagine this was not there. Let's kind of multiply and divide by this particular thing. So let me divide by d. Sorry, let's multiply here. So it's this times integral d phi fast e to the minus s0 fast. And I'm going to divide by this number. S0 fast. We've not really done anything at this point. Okay. Oh, sorry. Point out if I'm making mistakes because. Okay. So this one here, we kind of gave it a name, right? So this was the partition function of the fast modes in the approximation that they did not talk to each other, these modes, right? So this is just Z0 fast. That's just some number. But now you can kind of assign meaning to this, right? Because this is like one of the partition function. This is some probability weight, and that is some observable. Okay, so we can reassign kind of a meaning to this by saying, well, this is nothing but the expectation value of this observable, where the probability distribution is given by S naught. Is that fine? This is my sum over all possible events. This is my probability distribution. This here just normalizes that probability distribution. So that is the partition function, but that's just a normalization constant. right? And then this here is the observable that I'm trying to measure. So this quantity is nothing but the expectation value of e to the minus SU, slow fast modes, in the partition function that is over fast modes and 0. Okay, so non-interacting fast modes over which I'm going to do this calculation. So Z here is going to be Z naught F. That's just a number. I can pull it out. It's integral d phi slow e to the minus S0 slow. And now this expectation value, we can try and say, well, if U is small, or these nonlinearities are small, I want to try and do perturbation theory in U. And U just appears as a prefactor, right? So it's U times some phi to the 4. So this SU has this prefactor of this is U, and we are assuming that U is small and going to do perturbation theory in this. Okay. So this quantity here, we could rewrite it as 1 minus S SF U plus 1/2 SU SF square and so plus minus whatever, right? This entire is just some exponential series. You can write it out, right? But you say, well, that's not good enough. I want to be able to compare actions before and after. Okay. And so what this is going to do, if I integrate over the fast modes, right? What is this going to do? It's going to give me something that still depends on the slow modes in the problem, right? So it's going to give me 1 plus something that depends on slow modes plus something else that depends on slow modes and so on. Okay. But that doesn't look like the exponential of anything yet, right? It just looks like some series here. Okay. So the way we are kind of going to compare, what happens to the action when I integrate out is to say, well, I should take this entire thing and put it back in an exponent, right? So we have to kind of write this as Z0F times integral d phi S e to the minus S0 slow, okay, times the exponential of the logarithm of 1 minus SUS F plus 1/2 F. F. That's fine. So I have to kind of take my, this infinite sum, and this thing is that, I'm doing perturbation theory, so these terms are smaller. Okay. And now I have to take the log of that entire expectation value, and that will give me a definition for what this action is. So S0 of slow, S0 effective, the effective, sorry, was there a question? Okay, so S0, the effective action for the slow fields is going to be the old action for the slow fields, which is this, okay, minus this entire thing here. And if we could compute this, then I could try and read off, how these different coefficients are scaling, or what is happening. So let's try and kind of do this to some few leading orders. Okay. So let's try and do this to just order U for a second, right? So what is this going to look like to order U? Okay. This is going to be S0S. Sorry. I don't know why this is. this is not S0, right? So S effective. So the effective action for the slow fields, okay, is going to be given by the bare starting action for the slow fields, okay, minus, of course, if I do it to U order 0, then of course this is log 1, nothing happens, right? So I keep kind of minus log of 1 minus S U slow fast, spelling it fast. This, right? This is approximately 2, okay. And this now is going to be S0 slow minus, and now I'm going to ignore, so this is going to be just log of 1 minus SU SF with respect to 0, right? The expectation, U in U, yeah. Right. So this log, I mean, this expectation value of 1 is just 1. So I'm end with 1 minus log of 1 minus something. And to order U, this is just S0S minus log of 1 minus X is just going to be minus X. So this is going to give me something where I pull out this SUSF, where I have to average over the fast mode 0. So if you think in Hamiltonian language, this is just saying, oh, it's the unperturbed Hamiltonian plus sort of the, I'm taking some expectation value of the perturbation that gives me the shift in energy roughly, right? So that's kind of the form that we're getting here. Okay. If you go to order U square, you have to do two things. You have to kind of keep the second order term here. Okay. And when you expand the log, you can't stop at leading order in the expansion of the log. You also have to do this log of 1 minus X. You have to kind of expand it to all powers in X and just keep things to order X squared. Okay. So you have to do two things. One is kind of keep more terms here. And second, when you expand the log, you have to go to one higher order in the expansion. And the expression then looks like the following. So you can kind of do this. You get S0S plus, SUSF F0 I'm running out of space here. Let me write this last term down. I hope it's visible in the back. Sorry, to this order this, that's it. So this also looks like, so this is nothing but, this is like the, like root mean square kind of, what's the standard deviation of this object, right? And again, this looks like what you might have gotten if you were to do like second order perturbation theory. So imagine you do this in quantum mechanics. We know, first of all, that, the energy is always lowered in the second order. So imagine you have like two levels, the energy is kind of lowered in a second order perturbation theory, and it takes this particular form in this case. And so this, this expansion is what people call a cumulant expansion. If you kind of do it, you can do this to arbitrary orders. Okay. And what we've written down here in some sense is the average and the second cumulant of this particular quantity. But you can go to higher orders if you do this. You can kind of systematically write down higher orders in this expansion. Okay. I'm going to erase stuff here. I don't need this either. I'm going to erase this instead. And do people have any questions here? Otherwise, I'm going to just erase this stuff. All right. So this then tells us that, here I have like a systematic way of computing, and we've stopped here at second order, but you can go to higher order. A systematic way of computing sort of corrections to the bare action for the slow modes by incorporating the effect of the fast modes order by order in the nonlinear interaction. Okay. So let's write out sort of what this does to leading order, and then we'll kind of more or less, in some sense, guess, just given time, we'll kind of guess what the answer is here. Okay. So let's try and compute this quantity. Okay. I'm not going to write out S0 slow explicitly. I'm just going to call it S0 slow. Okay. But we want to kind of compute this one here, okay, as you. So what is this SU? Okay. So SU schematically, remember, was U times an integral over 3 momenta, and it had something that looked like this. Okay. I'm going to replace each of these phi's by slow plus fast. Okay, and I have some labels that I had. And now I want to integrate this, sorry, take the average with respect to all the fast modes. Let's see. So what are the things you're going to get from here? You would say one term that I get, which we actually kept when we were doing the previous analysis, was the one where all the slow modes enter and the averaging doesn't do anything, right? So you're going to get one term, which is an integral over Q1, Q2, Q3 of phi slow, phi slow, phi slow, phi slow. Okay. And now you see that because these are slow modes, this thing has to only go from 0 to beta, because none of these modes have weight at high energies or high momenta. The next term is where you say, well, 3 of these are fast and, 3 of these are slow, and let's say one of them is fast. Okay. And there's a whole bunch of these, the fast mode could be this one, this one, this one, or that one. So there's 4 different types of terms, but let's write out, one of these terms and see what happens. And let me not impose sort of cutoffs and so on yet. Okay. But let's imagine that I get something like phi slow, phi slow, phi slow, phi fast. Okay. Then you say, well, the averaging doesn't act on these, right? So the averaging only acts on this one. Okay. And there are many terms of this sort, right? So this is kind of just a schematic way. I've kind of just written one of them. Let's say it's, alpha. Sorry. So if you do this, then the question is, what happens to the fast mode average of phi f? So what's the answer for this? Sorry, for students, the only reason I'm asking this question is it's a simple question that doesn't need calculation. 0. Why is it 0? Sorry? Correct, right? So there is, I mean, so this just is the average of a field, right? This is like average of x, but the distribution is like e to the minus x square, right? So the distribution is even under phi going to minus phi, and I'm trying to calculate the average of something that's odd under phi going to minus phi, right? So such averages will vanish. And if you think about it, the reason, you can safely set it to 0 here. So this you might have said, well, what about broken symmetry? Okay, where we said, well, you just had a theory which had a Hamiltonian which was invariant under m to minus m, but then you said, oh, expectation value of m was not 0, the magnetization was not 0. But there you see that the reason that worked is because we had all the modes in the problem, including m equal to 0, or sorry, q equal to 0, and the uniform magnetization mode was this kind of critical mode associated with symmetry breaking in the problem. Okay, and we said we have to do something special there. We had to take some kind of thermodynamic limit, and you say, well, if I start here, I'll never be able to switch to the other side, or I have to put in a small field that puts me here and see that I will never get out of there when I take the thermodynamic limit. Okay, so I have to do something fairly special to get symmetry breaking. Okay, but this quantity, the fast modes know nothing about symmetry breaking in the problem. Okay, so it's perfectly safe to kind of take this and set it to 0 using exactly the reason that you just said. Okay, so this vanishes, and you see immediately that, okay, that means that even if I have 3 fast modes, I can use the same argument, right? So if I have something like, u times integral, fast, slow, I can also set this to 0. Sorry, this will have, the expectation stops there. This will also vanish, right? So the only thing I really have to worry about is things where, 2 of these modes are slow and 2 of them are fast. Okay, and there are many terms of that sort, because clearly I can take one term which is like slow, and a fast from here, right? And there are many such terms. So let's write out, one of them, and then, I'll just put dash for the rest, right? So there's some Q1, Q2, Q3. There's a phi slow alpha, let's say. Then there's a phi fast beta, and the phi fast. Okay, this will be one type of term. Okay, I also have terms where, I take the slow field, one of them from here, one of them from there. So let's write out one term of that sort. So that will look like phi slow alpha, phi slow beta, and something like phi fast alpha, phi fast beta. And there's many terms of this. Okay, so the question is now, how do I calculate quantities like this for a Gaussian? So what we want to compute is the more general one. So this is both betas are the same. Let's take alpha and beta to be of this form. So we have phi alpha fast with some momentum Q1, phi beta fast with some momentum Q2. And I want to calculate its expectation value. So this quantity, you would say, I can just do this integral. I have to integrate over the fast modes, e to the minus something that has, 1/2 integral over q t plus kappa times q square times phi fast q phi fast of minus q times this quantity here. and suitably normalized. So let me just call this 1 over some normalization factor that I have to, which is the integral without those terms. And this, I'm going to kind of write the answer, but you can kind of guess that this was like e to the minus some alpha by 2 times x square. I'm going to calculate something like this. Then you see that unless, sorry, this is alpha and alpha, or no, mu, right? This is some dummy index that I'm summing over, but it's the same index here, right? You see that quantities like this, for every mu, I can independently just change its sign for every component, and this Gaussian is unaffected, right? Whereas if alpha is not equal to beta, and I do this, then clearly this quantity will average to 0 because it will flip sign. So it will be odd, under any one of the components. If these two components are not the same, alpha and beta, this will vanish because I can independently flip the sign of each component here without changing the weight. Is this fine? So I know that alpha is to be equal to beta. The same thing here also in terms of momentum, because here q and minus q appear together, right? So if I change phi q by, let's say, -1 and phi minus q also by -1, right? But then I do it randomly for every q, right? Then you see that, this quantity doesn't change. But if q1 and q2 are different, then only one of them will change sign and not the other, right? So this quantity here vanishes unless alpha is equal to beta and q1 is equal to q2. Okay, and then it looks like the expectation value of something like e to the minus alpha x square, and I'm calculating x square expectation value. Okay. So the answer for this just turns out to be 1 over t plus k times q square. Right. So this, this controls, the spread here controls sort of what x square expectation value is, and just on dimensional grounds, it will be 1 over this prefactor here, and you can work this out. Okay. And now I have to put in kind of the fact that alpha has to be equal to beta. So this will have a factor of delta alpha comma beta, a Kronecker delta for that. And it will have a delta function for q1 to be equal to minus q2. So there will be a factor that turns out to be some factor 2 pi to the d times Dirac delta of q1 plus q2. Okay, sorry, I'm already out of time. So why don't we do maybe one thing I could do is maybe I'll try and switch and see if I can kind of write slides or something for tomorrow, and not for tomorrow, for Friday. So then we can kind of speed up, I can, go through these calculations step by step on slides so that it's a bit easier, or at least I have some notes which I've kind of written out, which Sanjeev said maybe it can be posted on the same website. So that will be useful. And then maybe I'll just do slides for this, and then we can. But just to kind of maybe, can I take like a few minutes and just finish this part? Okay. So this SU that you get to leading order then turns out to be kind of this correction. Sorry, this was the fast 0, right? This thing here. Okay, you see contains quadratic terms in the slow modes. Okay, and let me write out sort of what the answer is here. So it's going to be u because of this prefactor of u. Each of these gives me a factor of 1 over t plus kq squared. So I'll get something like 1 over t plus kq squared from there. Okay. Now factors like this are going to be different from factors like that, because here my Kronecker delta with beta is always satisfied, right? But I'm summing over beta. So these kinds of terms give me a factor of n, where n is the number of components. Okay. Factors like this just contain a delta function of alpha and beta, right? But alpha and beta are going to be fixed kind of by my things here. So I can choose my alpha beta for the slow modes, then this is completely fixed. So I could choose alpha equal to 1, beta equal to 1. Then this will give me something non-zero, right? But this doesn't contain an independent sum over alpha and beta because that's governed by what's happening to the slow modes, okay? So you get factors which correspond to factors of n in cases like this and no factors of n in cases of this sum, okay? So you have to distinguish two types of terms. And so what you get from here is you see from here that there are 6 types of terms that appear here where I have to pick 2 fast and 2 slow modes out of here. And I have to do this for the case, so here I basically have, 6 possible choices that I can make from here, right? I have to pick 2 out of 4 and call them slow. And the remaining I'm going to call fast. So there are a total of 6 types of terms I'm going to get that are going to contribute, okay? Of which some of them will look like this, where betas are the same, right? And you can kind of read off which of those these are. So if I have 2 of these picked to be fast, I'll get a factor of n. If I pick these 2, I'll get a factor of n. But for any of the other 4 combinations, I don't get a factor of n. Okay. So let me then write out sort of what the answer is. Then maybe we can go into details next time. So this 2n plus 4 comes from there. 2 terms have a factor of n, and the remaining 4 don't. So that's kind of all the 6 terms, 6 types of terms that we have. And then finally, we'll end up getting things which look basically like these slow modes left over. So you get, an integral over q over slow modes, phi q, phi minus q. And because these are slow modes, the answer is going to go lambda over. Okay. So remember that there are 3 momentum integrals here. 2 of them are going to get fixed by, relatively fixed by the fact that this momentum has to be the same up to a sign, right? And so you're going to be left over with one momentum integral, which looks like this. And I don't think there's anything else. Yeah. Sorry, there is one. Sorry. Sorry, I'm left with sort of one more thing that I have to do, which is I have to do this integral over, let me call this some q2. So this was just coming from this expectation value, but I have to also integrate over the momenta. And so there's one momentum integral that's left over. So I had 3 momenta, one of them got constrained. So I have 2 momentum integrals. One of them is here, and the second is a momentum integral that I have to actually do, but this is over fast fields. And so this momentum integral over q2 runs from lambda over b. Is this fine? This expression, and you can kind of work it out in detail. But okay. So what you see from here is that to leading order, what has happened is that these are some numbers, this entire thing, right? This looks like the action that was multiplying T, the reduced temperature in my bare action S0, right? And so what we have is a correction to the reduced temperature, and the correction to the reduced temperature is some positive number, right? So if you thought T was positive, it's going to become more positive now, right? So what these interactions do is they've kind of, what you thought was ordered, let's say, you thought T was a little bit negative or T was 0. In fact, this is going to renormalize the value of the temperature and make what you thought was ordered, it'll actually make it disordered. Okay. But eventually, if T is sufficiently negative, of course, then this will still give you a phase transition. So the location of the phase transition has moved because of this correction to the reduced temperature. Okay. And we'll kind of write this out in flow equations and do this next time and write out what the second order term is. Okay. So I'll stop here and then maybe we can continue. I'll do this on slides maybe on Friday just so that it'll be better. Yeah. No, we just assume that U is small, that I can do perturbation theory in U. Right. So what are we doing perturbation theory? Right now we are doing assuming that I can do perturbation theory in this bare quantity U, right? And we'll see that, clearly if this U were to start flowing, then this would not make sense, right? And so we have to ask, is this perturbation theory really valid at all at the end of the day, right? But right now we're just doing perturbation theory in U without worrying about OS with respect to what or yeah. Correct. So right now this just looks like a correction to kind of the Gaussian description, right? So this just corrects the reduced temperature. And when we go to the next order, we'll see that in fact there will be a correction also to the interaction. Sorry, I'm kind of going much slower than I thought I would, but maybe it's fine. I kind of had this, I think, overly ambitious outline. Yeah, that's fine. Maybe we'll see. I don't know how far. I mean, this calculation will kind of definitely wrap it up, at least in the first bit of the next lecture. And then maybe at least I'll kind of outline or maybe just mention a bit about things that I was intending to do, but I don't think we'll get really a chance to. That's fine. Okay, I'll stop here. So if people have questions, we can chat, but otherwise.
There were two first term in this case. Including that term.
4 fast terms, yeah. So that's also there, but that I'm going to say that that's just a number. Correct. So it's a number, but it doesn't actually modify the action for the slow fields to the Gaussian or to any of the slow field properties. Correct. So at order U square, what we will find is that there are terms which the specific terms that we'll want to do at order U square is a term that will correspond to, 4 of them being fast and 4 of them being slow. Right. So now we'll have 8 fields and we want to do 4 fast, 4 slow. But I'm going to kind of fudge it a little bit given the time. Yeah, I'll kind of.